So hi everyone, thank you so much for joining this session. This is the last session in module 5, where we are talking about the advanced features and standard extensions for the .11 protocol. We went through Wi-Fi 4, 5, 6, 5, 6, 6E, and now the last session in this module is about Wi-Fi 7, which is quite exciting. And with this module, we come to the latest standard that is out there. And in today's session, we'll talk about a number of things related to Wi-Fi 7. So before we do that, let's quickly recap what we talked about in last session. Last session was about 6 gigahertz. We talked about 6 gigahertz channels. We said that there is about 1200 megahertz of contiguous clean, not necessarily clean, but continuous spectrum that is available for unlicensed use, that is opened up for Wi-Fi. And this is now very exciting because a lot of Wi-Fi devices can operate in the spectrum. But there are certain rules because there are certain incumbents that are using this technology. So all the equipment that is used in the 6 gigahertz band need to follow certain rules. And there are certain device classes like low power and standard power and so on. So we talked about that. We talked about AFC and the rules required to follow for basically using certain bands in outdoor environments. And we talked about how that works. We talked about the main use cases where Wi-Fi 6E is used. We said that it is mostly going to be used in certainly for access, but also for backhaul connections and mesh links and so on. And with the 1200 megahertz wide spectrum becoming available, which means that it opens up so many channels. So we said that there are about 59 20 megahertz channels, which is a lot more than what we have in the 2.4 and the 5 gigahertz band. So when we have so many channels, that opens up new challenges when it comes to channel scanning. And so the traditional method of channel scanning doesn't really work anymore in Wi-Fi 6. And so we talked about new channel scanning methods, both in band and out of band. So we covered things like fills and preferred channel selection and reduced neighbor reports. We discussed that in detail. We also talked about interesting features like multi-PSSID, where within a same beacon, we can advertise multiple SSIDs and PSSIDs. So if you missed that session, that recording should be now up on our website. You can go back and watch it. All the slides and everything should have been updated. If you're joining us for the first time, you can access the course webpage from this link. You can register to these webinar sessions to get updates from the QR code in the middle and the link in the middle. And if you're interested in joining the WhatsApp group where we provide regular updates, you can do that as well. Okay, so now jumping into the slide that I have been using for the last 4 sessions. So as I said, we talked about Wi-Fi 5, what's new in Wi-Fi 5, and then we went to Wi-Fi 6, and then Wi-Fi 6E, and now in Wi-Fi 7. So the main features in Wi-Fi 7 we're going to talk about relating to a number of enhancements both in the physical layer and the MAC layer. So Wi-Fi 7 is basically the marketing term, but the standards terminology is 802.11be, which is, if you remember Wi-Fi 6, it was 802.11ax. So now we have 802.11be, and it is normally now referred to as Wi-Fi 7. So Wi-Fi 7, if you remember Wi-Fi 6, 11ax, it was about high efficiency. So we wanted to not necessarily focus too much on throughput improvement, but we wanted to focus on being able to support lots of devices and get better spectral efficiency and using multi-user MIMO, using OFDM technologies and so on. Wi-Fi 7 wants to do all of that, but also wants to increase throughput. So Wi-Fi 7 is now referred to as EHT, or extremely high throughput, because now we are shooting for 5 times more throughput than what we got from Wi-Fi 6. Along with extremely high throughput, the objective of Wi-Fi 7 is also to achieve very low latency on latency specific devices that require very low latency, like AR, VR applications, real-time gaming applications, and so on, which require low latency. We want to support that, and also want to support really high reliability in multimedia, basically for IoT devices when you have edge of the cell situations where you have lots of IoT devices. We needed high reliability. So these are the kind of main objectives for Wi-Fi 7. So how do we achieve that? By adding a lot of features. So this is why Wi-Fi 7 is really cool for anyone who's following the standards. Like me, I've been following the standards for the last 15 plus years. And in this standard, there are so many new things that have been added, which are all very cool in theory. Practically, we have to see how well they all work. But there are a number of enhancements at the physical layer to increase the raw data rates. Like we have 320 megahertz channels, we have a 4K QAM modulation rate, we can go up to 16 by 16 MIMO, and then we have EHT preambles, and we have also some physical layer improvements to improve the efficiency, like preamble puncturing and multi-RU support. These are targeted towards the efficiency, but then there are also other features for raw throughput. Those are the physical layer enhancements. And then we have the MAC layer. There are lots of really new exciting things. Probably the most exciting one is what we refer to as the multi-link operation, or MLO. We're going to talk about that in detail. And then there is also other features like multi-AP coordination, which is more for enterprise class access points. So, and for enterprise deployments, and there are lots of cool features there as well. So we'll try to cover as many of those as we can in this session. So again, just to summarize, 320 megahertz, 4K QAM, 16 special streams, MLO, and multi-RU, and all these other things. So this picture, I found it very interesting when I was reading one of the papers that I found online. I had this picture. It's a more fancy kind of way of basically listing all these features. So I really liked it, so I put it up here. But again, these are some of the things that have been in consideration and also being implemented in Wi-Fi 7. So all these features that I just talked about. So starting with the most simplest one to understand. So that is the 320 megahertz channels. So the concept is very simple. With up to Wi-Fi 6, we went to 160 megahertz channels. Now we are doubling the channel bandwidth for a single user to use up to 320 megahertz. And why we are able to do that? We are able to do that because we have the 6 gigahertz spectrum available now. So we have 1200 megahertz wide of channel bandwidth available. So now we can afford to do 320 megahertz channels. So if you do some simple math, you can see that we can support up to at least 3 non-overlapping channels in the 320 megahertz band. Now, 320 megahertz is really more for residential use, and it's not really a feature that is very practical in enterprise, because the enterprise is all about deploying lots of APs, high density deployments, and so on. And if you're using 320 megahertz channels, then you will not get many overlapping channels, non-overlapping channels. So it's not very practical in enterprise deployments, mostly 40 megahertz, 80 megahertz. Maybe in around some rare situations, you can go to 160 megahertz. But 320 megahertz is really more for residential use. Right? And if you see how the technology evolved, most of the initial part of the standards products that come out are going to be for residential use, because residential deployments are probably a larger market for Wi-Fi. And so if you look at all the Wi-Fi 7 APs that are available in the market right now, most of them, initial versions were all residential. Now we're starting to see enterprise class access points being released as well. But 320 megahertz is more for residential. Now there is this other new feature about 16 special streams, where you can have up to 16 transmit antennas and receive antenna chains. That is, again, this is a very impractical feature. Most likely no one is going to implement it. Maybe some rare occasions, but it is going to be very expensive, very complex in terms of power and complexity to design a 16 by 16 MIMO access point. But that is a part of the standard. So most implementations that we'll see are still most likely going to be 4x4 or 4x4, even for Wi-Fi 7. Maybe in some cases you will see 8x8, but 16 by 16 is really not practical. The other thing which is more practical in the physical layer is the 4K QAM, which we are already seeing in a lot of the testing that we're doing. That is a feature that works. So what is 4K QAM? Of course, we are trying to go into even higher order modulation rates. So Wi-Fi 6 was 1024 QAM. now we go up to 4096 QAM. Right? So which means that you are encoding more bits per symbol. So if it is 10 bits per symbol in Wi-Fi 6, now you're able to do 12 bits per symbol in Wi-Fi 7. So we are packing more and more information as we modulate the bits on the signals. And of course, that will give you more throughput, more data rates, but less reliability. And 4096 QAM is expected to really only work for a few feet away from the access point. But interestingly enough, from all the testing that we have been doing recently, we have seen that 4096 QAM actually does work even in the real world, even at a decent distance from the access point, which was quite nice to see. So if you look at the three new things that are added, 320 megahertz channel bandwidth, 4K QAM, and 16 by 16 MIMO, that if you add all of those combinations, now with Wi-Fi 7, theoretically, you can go all the way up to 46.1 gigabits per second 5 data rates. That's almost 50 gigabits per second physical data rates on a wireless link. And that is just amazing, at least in theory, which is 4 times more than what we have with Wi-Fi 6. Now, this you will only get when you're doing all these combinations, 320 megahertz, 4096 QAM, and 16 by 16. Now, if you look at how the MCS table changes, so this is the MCS table for additions for Wi-Fi 7. This is only for single spatial stream. Of course, if you go all the way up to 16 by 16, this table becomes much bigger. So you can see from this table that MCS 12 and 13 got added, and there's also 14 and 15. So 12 and 13 are enabling 4096 QAM. MCS 12 will be 3/4 coding rate, and MCS 13 will be 5/6 coding rate. And at full 320 megahertz channel bandwidth, at the shortest guard interval setting, you can get theoretical phi rates of about 2.8 gigabits per second with one spatial stream. So now, if you're doing the same thing on 16 spatial streams, now you multiply 2.88 by 16, that will get you the 46 gigabits per second theoretical phi rate, right? That's what's possible. But again, that's not really practical. Most solutions implementations will be 4x4, which means that the theoretical phi rate can go up to 4 times the 2.8 gigabits per second. And in our testing that we have seen, most stations that we are using are 2x2 MIMO stations. So if you're looking at throughput, then you're using really only 2x2. And we were able to see the physical data rate of 2x2 would be about 5.6, 5.4, 5.6 gigabits per second. And the actual throughput that we are getting in our testing is close to 5 gigabits per second, which is still very impressive. We are able to get, under ideal conditions, get 5 gigabits per second throughput, close to 5 gigabits per second throughput on a Wi-Fi 7 link in 2x2 MIMO mode, which is pretty awesome. Now, they also added MCS 14 and MCS 15, which is interesting because it's MCS 14 and 15 are not about throughput, it's about reliability. So the idea of MCS 14 and 15 is to handle what we refer to as edge of cell scenarios, when you have a device which is at the edge of the cell, and let's say it is like let's say a wireless camera, surveillance camera that's basically in your balcony or something, and it doesn't have very good signal from the access point, but it still wants to communicate with the access point and send a certain small amount of information. You can use this what we refer to as BPSK DCM mode, which is MCS 15. DCM stands for dual carrier modulation, right? So what this is doing is it is taking MCS 0, which is your standard BPSK, and it is adding redundancy. So let's say you are transmitting over 26 tones in an OFDM situation. So you duplicate each tone, you actually use an extra tone and communicate the same information. So if you really need 26 tones, you're actually using 52 tones for communicating. So you're duplicating the information across the tones to get extra redundancy, right? And what then happens in the frequency domain is if you use this chunk of frequency and then duplicate the same information in another chunk of frequency, if there is some interference in this area, you should be able to still get the information across by using these frequencies. So by adding redundancy, duplicating the data, you are making the communication more reliable, even though you're dropping the throughput. So you can see MCS 15 is cutting the physical data rate by half. So if you're able to get 144 Mbps with MCS 0 in BPSK, you're getting half of that with BPSK TCM. And there is another mode called modulation type called BPSK TCM DUP, which is again another level of duplication. So not only are you duplicating the information across tones, you are taking the entire information and duplicating it across frequency bands. So now you're duplicating it 4x, right? So now your throughput or your data rates is going to drop even more to 36 Mbps, but it is going to give you even more reliability. So those are MCS 14 and 15. It's yet to be seen who is going to use it. Most likely IoT device makers would most likely use that because they don't really need very high throughput, but they need very good reliability. So those were introduced in the standard. Okay, so when we look at the physical headers, now if you followed some of the previous sessions, we talk about backward compatibility. So one of the coolest features in Wi-Fi is any new technology supports backward compatibility. So let's say you have a phone, and my phone is like, let's say 3 or 4 years old. When it connects to any Wi-Fi network, it doesn't have to worry about is it a Wi-Fi 5 access point or a 6 access point or a 7 access point, because we know that most access points deployed, even though they are using the latest standard, will be backward compatible. And so I don't have to worry about that, right? So that's one of the cool features of Wi-Fi in general. So the same backward compatibility feature functionality carries forward to Wi-Fi 7. So which means that in the preamble, you will have the legacy basically training sequences, so that the legacy devices can do signal detect and identify dot level frames using the legacy preambles. And that information is still part of the Wi-Fi 7 EHT preamble. But then there are some new fields added. There's something called as a USIG field, or a universal signal field. And the idea of this field is to provide basically some fields that are used by all standards, across all standards, like bandwidth information, uplink, downlink, transmission opportunity durations, and things like that. And the USIG field also contains basically is designed for forward compatibilities, which means that all future standards should be able to identify the version without having to actually go through the entire training sequence. They can look at what we refer to as a physical version identifier, or a 5 version identifier, that is a field. And based on the version identifier, they can identify if it is Wi-Fi 7 or maybe Wi-Fi 8 or maybe Wi-Fi 9 in the future, right? So there are some fields that are added to the USIG field, and also we have the EHT, or the extremely high throughput signaling field, that has all the extremely high throughput specific information relating to multi-link operation and multi-AP coordination, a number of other features. So there are all these other informations in the EHT signaling. So let's talk about another interesting cool feature called preamble puncturing. Again, this is also a physical improvement. Again, this is not trying to improve throughput. So we looked at 320 megahertz and 4K QAM and 16 by 16 MIMO. All of them are trying to increase your data rates, throughput. But preamble puncturing is trying to improve your efficiency in how you access the channel. So for example, let us say you have an 80 megahertz wide channel that is allocated for a particular access point. And when the AP is doing the signal detect, it detects some interference in some part of the 80 megahertz, maybe a 20 megahertz piece of the 80 megahertz. Normally, what APs or stations will do is they will back off and they will not use the entire channel, and that is basically wasting your the frequency resources. So what if we can say, I am still going to use that 80 megahertz channel, but just not use that 20 megahertz portion that is causing interference or that is being used by someone else. So what we can do is we can puncture that particular smaller band across the wider band and transmit across the other bands, right? So the way the puncturing works is, let's say you have an 80 megahertz channel, we send preambles on each of the 20 megahertz pieces of that. So there are 4 20 megahertz pieces, so we send preambles on all 4 of the 20 megahertz pieces. When we're doing puncturing, we can say on the first part, I will send the preamble. Second part, I'll send the preamble. Third part, I will not send the preamble. and then the fourth part of it I'll send the preamble. So you're basically not sending the preamble in one portion of the band, and that indicates to the receiver that we are going to use the 80 megahertz channel, but except for that 20 megahertz portion in the middle, and we're going to puncture that and transmit over the remaining 60 megahertz, right? So that allows us to use channels that wideband channels that have narrow band interference. Okay. This is also can be very useful when you are complying to DFS and AFC requirements. So let's say you are operating in a 20 megahertz wide channel in the 5 gigahertz band, and you see DFS interference on only in a 20 megahertz piece of that. Rather than moving off of the channel completely, you can puncture that 20 megahertz and still transmit over the remaining 60 megahertz. And similar things we can do for AFC. And again, this improves the efficient use of the spectrum that is available. Another interesting feature with Wi-Fi 7 is what we refer to as multi-RU OFDMA. So for those of you, if you recollect, basically, if you watch the previous sessions, we talked about something called as a resource unit or an RU. RU is nothing but a set of tones in the spectrum. So let's say you have an 80 megahertz channel and you want multiple devices to use the 80 megahertz channel. So you can divide the 80 megahertz channels into smaller chunks and allocate them as resource units to multiple users. An example is, let's look at this pie chart here. Let's assume that this entire pie is 80 megahertz. You can take portions of that, different sizes, and allocate it to different users. And each one of them can be considered as a RU, right? Normally, what we do is each station gets only one resource unit. Now, the resource units can be different sizes, just like what you see in this pie chart. One resource unit will be 30% of the 80 megahertz band, another resource unit could be 40% of the 80 megahertz band, and so on. But each user gets only one resource unit in the normal OFDMA, right? But if you're using multi-RU OFDMA, then you can, a normal user, a single user can get multiple RUs. So why is this important, right? So for example, let us say I need a certain amount of the spectrum. So for example, I need 35% of the spectrum, right? So I can go for, the AP can allocate a 40% RU, which is more than 35%, which is more than I need. I don't need the full 35 for 40%. So the remaining 5% I have to do some padding, and that's wasting the extra bandwidth. Or the AP can allocate 30% of the basically spectrum, which is less than what I need, right? And so I'm not able to fully transmit my data well. What if I can pick two RUs, right? So one 30% RU and one 7% RU. Now I have 37%, which is closer to the 35% I want, right? So by allocating multiple RUs, and especially the RUs, the smaller RUs that are not going to be used by others, you're now combining multiple RUs to get more options to actually use the exact amount of bandwidth that you need to transmit, right? So basically, if you look at this example in Wi-Fi 6, user 1 can get this RU, user 2 can get an RU3, but RU2 may not be allocated to any user, right? It's free. So in Wi-Fi 7, you can, if needed, if you need more bandwidth than RU1 and less bandwidth than RU3, then you can combine RU1 and RU2 and do multi-RU communication, right? So in technical terms, you can actually combine multiple tones, multiple sets of tones to get MRU communication. So if you look at this picture here, the standard OFDM Wi-Fi 5 uses the entire spectrum, y-axis being frequency and x-axis being time. The entire spectrum is used for each user. In the case of OFDM-A, there are multiple users that can use one set of frequencies, but each user gets only one RU. But in the case of multi-RU, you can have user 1 or user 3, for example, gets a 484 tone RU plus another 242 tone RU. So they're getting multiple RUs. And this is again helps in more efficient use of the spectrum that is available. Of course, it increases the complexity a lot when it comes to implementation, but when it comes to the efficiency, it can certainly provide better efficiency. Okay, so those were mostly the physical layer features. To summarize, we talked about the 320 megahertz, 16 by 16 MIMO, and also 4K QAM. All three of them will increase your data rates and throughput. And then we talked about preamble puncturing and also multi-RU support, which will allow you to use the spectrum more efficiently. So these are the physical layer improvements when it comes to Wi-Fi 7. So now let us talk about the MAC layer. So there are many major MAC layer improvements. One of the most exciting one, and the one that is already being implemented, is what we refer to as multi-link operation. So what is multi-link operation? So most modern access points and stations might have multiple radios. You can refer to them as bands or links. So in this terminology, we're going to refer to a frequency band or basically as a link, right? So now you can have stations with dual band and tri-band radios. Each one of those bands can be referred to as a link. Even though there is one radio, you can have two links on that radio, right? So the idea here is when you have APs talking to stations and they have multiple radios, why not use multiple radios together to get more throughput, right? So far, anytime a client associates with an access point, and the client can basically scan on one channel, let's say a 2.4 gigahertz channel or a 5 gigahertz channel or a 6 gigahertz channel. Of course, it will scan through all the channels, but it can connect to the access point on only one channel at a time. Even though this device has multiple radios, it can communicate with the API on only one radio at a time, one link at a time. That is what we did up until Wi-Fi 6. Wi-Fi 7 now allows you to coordinate the communication and combine multiple radios on a transmitter to talk to multiple radios on a receiver to get even more efficiency and more throughput wherever you can. So that's a fundamental concept of multi-link operation. So just to take a real world example, I mean, some of you, if you're from India, you might have watched this movie, Three Idiots, and there is this professor in this movie who's highly efficient guy. And so what he does is he has this habit of writing multiple letters at the same time using two hands, right? Normally, when we write, we only use our one hand to write, right? Even though you're either left-handed or right-handed. But this guy really wants to write with both hands simultaneously. So if you take this example of his head being the MAC layer of the access point, and his hands could be the physical layer. So basically, there are multiple radios or multiple physical layers. If you want to be really efficient, you can somehow practice to use your one brain, but still write two letters at the same time with both your hands. And of course, that will increase your efficiency and increase your throughput. Basically, because you're using all the resources that you have for multi-link operation. That's fundamentally the concept of MLO. So some terminology when you refer to MLO that you will hear is one term that you will hear is the MLD, or it's nothing but the device that supports multi-link operation. So if this access point supports multi-link operation, it's called an MLD or a multi-link device. Under MLD, you have an AP MLD, which is basically an access point that supports MLD or which is a multi-link device. And you'll also have non-AP MLD, which is nothing but a station. A station is a non-AP, it's not an access point, but it supports MLD. It's an MLD, it's a multi-link device. So you have non-AP MLD and MLD as the terms that you need to know. There are also many types under MLO. There are single radio implementations and there are multiple radio implementations. So we'll talk about that. These terms that you might have heard, MLMR, MLSR, EMLSR, and all of that. So what are all those terms? We'll talk about that in a minute. Okay, before we get into that, let's just talk about a few benefits of multi-link operation. So one of the obvious benefits is increasing throughput. So for example, you take a situation where this AP has 3 radios, and let's say this station also has 3 radios, and the links are all available. There is no other interference, no other devices. Rather than this client talking to this AP only in 2.4 or only in 5 or only on 6, what if it can simultaneously talk on all 3 bands and essentially achieve much higher aggregate throughput? So of course, you can do throughput boost using the multi-link operation. We can also do improvement in latency. So by picking, rather than transmitting on all links, you can always dynamically pick a link that has the least interference and provides you the most bandwidth or most throughput. And dynamically you can change that, and that will improve the latency. For example, if a particular station is communicating over the 2.4 gigahertz band with the access point, it can at some point choose to switch from 2.4 to 5. Now, this is not the traditional load balancing or band steering. So we're all used to load balancing and band steering, where a station connects to an access point, let's say in the 2.4 gigahertz band, and after a while it decides to move to 5 gigahertz, or the AP might decide to de-auth the client so that the client can go to the 5 gigahertz band. That is traditional band steering and load balancing. In the traditional case, what happens is those links are separate. So for example, if this client is connected in the 2.4 gigahertz band to the access point, when it moves to the 5 gigahertz band, it has to most likely do a new association or a reassociation, and it has to create new security context, which means that it has to generate new keys, and it's almost like a new connection. That is not what is happening here. Here, the MAC is the same. There is nothing changing at the MAC level. This is a pure physical layer switch between radios. So you can actually move the station from 2.4 to 5 to get latency improvement. And at the MAC layer, nothing changes. It's still same security state, same MAC address, everything the same, right? And that will allow you to make more efficient spectrum. Of course, you can also use it for increased reliability. So let's say you're communicating over 2.4 gigahertz band and that communication failed because the link quality is bad. Then you try over 5 gigahertz band, failed. Maybe at 6 gigahertz band, it's successful. So you can basically use it for reliability, and also basically you can do redundant transmissions. So you can duplicate the same data across 2.4, 5, and 6 gigahertz band and send the same data across all three bands. Let's say 2.4 has too much interference, 5 has too much interference, and then maybe 6 is successful. So now you're sending the same data across multiple links, and you're increasing your reliability. And of course, you can also use it for traffic differentiation, traffic separation. If you can implement QoS, if a particular station needs better quality of service compared to the other, you can switch links based on the priority requirement. So these are all the advantages when it comes to MLO or multi-link operation. So let's take a simple example of how MLO, different types of MLO work. Okay. So if you take the example of basically a transmitter, which is an access point and a station. So the access point has two radios or two bands, 5 gigahertz and 6 gigahertz, and the station also supports 5 gigahertz and 6 gigahertz, right? So now they want to communicate with each other using MLO. So one method is what we refer to as opportunistic link selection. So that's the first in the diagram. If you see at the bottom, the first circle, that is opportunistic link selection. So what does that mean? So the AP and the station would initially try to communicate over, let's say, 5 gigahertz band, and they, or at least they sense the channel and see how good the link quality is, what kind of signal quality you're getting, and then they will do the same thing in 6 gigahertz band, and they will pick which link will give them better performance and better reliability. So you can actually pick between 5 gigahertz or 6 gigahertz. Remember, this is not like MAC level load balancing or band steering. This is happening at the radio level, right? So, and you can dynamically pick which link is better, and then that this way you get better link selection. That's one method, right? Link aggregation, which is the number 2 here, is another method. So now what you can say is, I am going to take my data that I want to transfer from the AP, and I'm going to send some of the data in 5 gigahertz and the remaining data in 6 gigahertz simultaneously. So now you're aggregating the 5 gigahertz link and the 6 gigahertz. So now you're getting more through. So link aggregation is one method for MLO. And then there is also a full duplex method where you can do simultaneous transmission and reception. So on 5 gigahertz, the AP can decide to send data to the station, transmit, and on the 6 gigahertz, it can receive data simultaneously. So now you get full duplex communication with MLO across multiple radios, right? So these are some of the things that some of the different variations of MLO that you have. Now looking at it slightly differently, so the basic modes of MLO, of course, we have a single link operation. If you look at a single link operation, there is only it's basically a single threaded operation where you have multiple packets to send. You will send one packet at a time. You will back off basically, and then you wait for interface space, then transmit. And so that's how packets are normally getting transmitted. But if you're using MLO, and under MLO there is something called as NSTR, or non-simultaneous transmit and receive. There is one method here where you can use multiple radios to simultaneously transmit, but there is one primary radio and one secondary radio, and you can only transmit or only receive across these multiple radios. You cannot do both, right? So, for example, when you are contending for the medium, you contend for the medium on the primary channel, and then you check that the secondary channel is also secondary link is also available. Then you can send packet number 1 on the primary and the link, and the packet number 2 on the secondary link. And that way you're getting better latency, low latency for packet number 2, right? So you can actually use multiple links to as one coordinated link to transmit more data. It's like link aggregation. Right? And again, you have this other term called STR, or simultaneous transmit receive, which is like the full duplex operation that I mentioned in the previous slide, where the two radios are operating independent from each other. So one radio can transmit and then one radio can receive. The problem with that model is it's a very complex implementation. If you take a device like this, and let's say there are two radios in it, and one radio is transmitting and the other radio is receiving, that is extremely complex to implement, because it will have all kinds of near field effects and all kinds of RF level, noise level problems because of the proximity of the radios, and it is much harder to implement. But of course, you get the better performance by doing that. Okay, so looking at MLO in a little bit more detail and on the terms that are normally used. So there is the single radio MLO technology, where the device wants to support MLO, but it cannot have multiple radios. It has only one radio. That radio can be a dual band radio. It can support 2.45 gigahertz or tri-band radio and whatnot, but there is only one radio on the device, right? So in that scenario, we have some technique called MLSR, or multi-link single radio operation. So here, what as I was saying before, this is used for better link selection. So the radio can actually sense on or read, basically scan on all the channels, and it will figure out which channel is best for transmission, and it will use that channel, and it will keep changing the links as needed over a period of time. There is this other method called enhanced MLSR or EMLSR, which is probably the most popular method that is currently being used. This is where you still have a single radio, but let's assume that the radio on this client is a 2x2 MIMO radio, which means it has two radio chains. So you can use one radio chain to probe and scan on the first channel of the AP, and the second radio chain 1x1 mode to probe and scan on the second channel of the AP simultaneously. Right, and then based on that, you figure out which channel is better for communication, and then you can send data in the 2x2 MIMO mode on the selected channel. So now the scanning process is more efficient using EMLSR, which is one of the techniques that is mostly used. If you're looking at multi-radio MLO, we have techniques called STR MLMR and NSTR MLMR. So again, it comes back to the same model where you have multiple radios. Now this device has multiple radios, and each radio could be dual band radio, for example. So now you're using, if you're using non-simultaneous multi-link multi-radio mode, then the station can transmit or receive over multiple links, but not transmit and receive at the same time. So it can either aggregate multiple links to transmit or to receive, right? So that's the thing that I explained before. If you're doing simultaneous multi-link multi-radio, here you can simultaneously transmit and receive across multiple radios. So you're potentially using all the radios, some radios to transmit and some radios to receive across the access point. And that again, this gives you the most amount of efficiency and throughput, but also the most hardest to implement. Again, there's also an enhanced multi-link multi-radio, which is probably even more complicated, where you can take a single radio on a station, which is 2x2 MIMO, and then use one radio chain on that radio to scan on one channel, another radio chain on that access point to scan another channel, and then pick the links and use them, right? So again, the technology gets more and more complicated, and as we go, and not all of them will be practically implemented. So, but nonetheless, it's very interesting to learn about these techniques. So to implement MLO, really, there is a fundamental change in how the MAC layer works. So now we have this concept of two MAC layers, what we refer to as the lower MAC and upper MAC. Remember the example I gave, the hands of the professor acting as basically the lower MAC, and then the head acting as the upper MAC, right? So the upper MAC is the common layer across the multiple lower MACs, and each physical radio will have one kind of lower MAC implementation, right, across the bands. So in the MAC layer, we have a single MAC address called the MLD MAC address, or multi-link device MAC address, and that is the MAC address that is used for all the communication across multiple links, right? And the same MAC address is used for connectivity, association, and is also used for security, all the four-way handshakes and other things that we do. That is the same thing that is used across the multiple physical layers. And also there is this interesting concept called, when we are implementing this MLO across multiple physical layers across the same MAC, there is this concept of packet level aggregation and flow level aggregation. So packet level aggregation is taking information coming from a single traffic stream and taking multiple packets from that single traffic stream and sending them across multiple links. So you get better throughput for the same traffic stream, right? So that's packet level aggregation. Flow level aggregation is where you take you aggregate at the flow level, which means that one link is used by one traffic stream and another link is used by another traffic stream simultaneously, right? This is specifically useful when you're doing like mesh backhaul, when MLO device 1 and MLO device 2 are forming a backhaul link, and then they are trying to send information across multiple devices, multiple source addresses and multiple destination addresses on the same link. And then you can use one source IP address and one destination IP address traffic flow to go through one link, and then another IP address, the source, another IP address destination to go through another link simultaneously. And this is also where you're improving your throughput. There are multiple methods that can be used here. So how do you connect to an access point that supports MLO? So how do you discover a multi-link access point? The most simplest method is all access points that support MLO will advertise their SSIDs on all the radios. Right? So for example, let's say this access point has a 2.4 gigahertz radio and a 5 gigahertz radio. It might advertise a 2.4 gigahertz specific SSID on the 2.4 gigahertz band, a 5 gigahertz specific SSID on the 5 gigahertz band, but the MLO SSID is advertised on all the bands. So you can see this example of a TP-Link access point. So in the 2.4 gigahertz, it's advertising a 2.4 gigahertz SSID, and it's also advertising an MLO SSID. Right? If you go scan the 5 gigahertz band, it will advertise a 5 gigahertz SSID, but it will also advertise an MLO SSID. So the MLO SSID is the common SSID for MLO connectivity across any bands. So to have a multi-link operation across multiple bands, you don't have to associate to multiple bands. You just have to associate to one band using the MLO SSID, and automatically you are part of the MLO connection, and then you can basically transfer across multiple bands. So in the connection process, we have this what we refer to as a new information element when multi-link association is happening. During the probes, authentications, association phases, these management frames now have this new information element called the multi-link element, right? So multi-link element is a new information element that will go in beacons, it will go in probe responses and association responses and so on. So the multi-link information element will have all the details regarding the multi-link operation at the MAC layer, right? So it has information about all the stations that are participating in the MLO operation. It has information about all the radios and that is respect to SSIDs and all the radios, so that the station can know what are the capabilities of the AP when it comes to MLO, right? And again, association responses and probe responses can have the RNR, the reduced neighbor report, plus the MLE information element, plus the EHT information element. So all these are all new information elements that will help in the proper MLO signaling as a part of the association and connection process. So again, to remind everyone, if you want to operate multiple bands between the station and the access point, you don't have to associate across all the bands. You have to just associate and go through the connection and security process on any one of the bands. And then that band, as long as you're connected to the multi-link operation SSID, you will get access to the multiple bands that are supported in that access point for multi-link operation. So that is MLO, and it can be a little bit complex and confusing, but certainly it's not easy for us to cover this in detail in 15 minutes. But you can certainly go to the references and maybe watch this video again, or watch some of the reference, read some of the reference material we provide, and they explain it in a lot of detail. So now talking about the next MAC level feature, which is more of an enterprise level feature where we have dense deployments. It's quite interesting, but again, it's not going to be implemented anytime. We're not sure when it's going to be implemented. We are still about to get the first set of enterprise class access points out in the market. So when we test them, we will see if this particular feature is supported or not. But it's a pretty cool feature. So if you look at a single wireless LAN cell, like so far, we are trying to get multiple access in many different ways. So let's say assume that this is a single access point and there is a cell around it, and there are multiple devices, stations trying to communicate. Okay, how do you get multiple access? One way to get multiple access is saying I have a certain amount of frequency band, and one way I can break it down into smaller chunks of frequencies and allocate some frequency to each device, and that is your traditional FDMA or frequency division multiple access, right? So you can do that that way, right? Or you can coordinate, or you can do it based on basically spatial reuse, where we are doing multi-user mining. So we can say station 1 is in this position, station 2 is in a very orthogonal position. So I can transmit to station 1 and station 2 simultaneously and get spatial reuse. Or you can do it based on time. You can say first time slot I'm going to send to AP1. I can go TXOP, that is basically a standard CSMA CA, or second time slot goes to station 2. So basically, you can get multiple access based on frequency, space, and time, right? But all the coordination is done by the single access point within a wireless LAN cell. So the coordination is between the AP and multiple devices that are inside the wireless LAN cell. So that's fine. But what if you want to do this coordination across multiple access points also? That's what multi-AP coordination is about, right? So what multi-AP coordination is saying is, if I have AP1 that is connected to station 1, and then in the same area I have another AP that is connected to station 2, I can coordinate across these APs either over the air or over the link or the wired link and say, okay, so to avoid interference, I can make this access point connect to this station using a certain set of frequency spectrum, and that second access point connect to the second station using a slightly different set of resource units, right? To avoid interference at that level. And the coordination is not done across the AP and the multiple stations in one cell, but the coordination is done across multiple APs. Now the same coordination can be done over space and over time, right? And that is what multi-AP coordination is about. It's a very, very cool feature. Of course, it's very complicated to implement, and there are some lower complexity methods like coordinated OFDMA, coordinated TDMA, coordinated spatial reuse, and there are more complex methods like coordinated beam forming and so on. So we'll talk a little bit more detail about that. So if you take the example of coordinated OFDMA, this is where there are overlapping cells. So you have cell 1 where you have AP1 connecting to station 1, and then you have another basically overlapping cell or OBSS where you have AP2 connecting to station 2. So what we can do is AP1 can now coordinate with AP2, and they already know that they are interfering with each other. They're about to interfere with each other. So AP1 can tell AP2, look, we are going to interfere with each other if we use the entire 80 megahertz band or 160 megahertz band. So why don't I use these RUs that are in the lower part of the spectrum to communicate with station 1, and AP2 you use the higher end RUs to connect to the station 2. That way we are using different frequency bands within the spectrum, and we are not interfering with each other, right? And so that coordination can happen across multiple access points, especially in a overlapping BSS kind of mode, and it reduces that connection time. The same thing can be done in space and also in terms of power. So again, if you have a scenario where AP1 is talking to station 1 and AP2 is talking to station 2, but the AP1 sees interference from this communication, right? So what the AP1 can do is it can communicate with AP2 and say, AP2, why don't you reduce your transmit power when you're transmitting to station 2? And then by the way, I will also reduce my transmit. So the AP1 will reduce its transmit power to communicate with station 1, and AP2 will reduce its transmit power to communicate with station 2. And so they are not necessarily overlapping with each other for that time instant. Now remember that this is dynamic. It's not going to stay like that forever. And it can change on a per packet or a per stream basis. And that's what makes it very complicated, right? This is not your channel planning where you do the channel planning once and leave it for the next several days. This dynamically is changing at a per packet or a per transmission opportunity level. And that's the reason why it is really cool and quite complicated. So similarly, you can do like joint transmissions, for example, right? So one of the things you can do is joint spatial multiplexing across multiple access points, right? So for example, the AP1 can communicate simultaneously in beamform to both station 1 and station 2 across multiple APs to transmit from multiple stations, and AP2 can also transmit to both station 1 and station 2 simultaneously across multiple cells without interfering with each other and beamforming. So again, when you're doing channel sounding and we are trying to figure out the beamforming patterns, you are not previously you're doing it only across AP and all the stations in the cell. Now you're doing it across APs also, right? In real time, right? That's what makes it very complicated. It can make the medium use very efficient. It can make it a lot less error prone, and it can definitely improve your signal to noise ratio and the reduce interference. But to implement that, it's going to be extremely complicated. You can also do coordinated beamforming, where AP1 can communicate with AP station 1 and AP2 can communicate with station 2 in such a way that the AP is beamforming the signal towards station 1 and creating a null towards station 2. That way, there is no interference. So AP2 will do the same. AP2 will beamform the signal towards station 2 and create a null towards station 1. And that way, these communications are happening simultaneously and they are not interfering with each other. Right? Again, this requires a lot of coordination between the APs. All the sounding that we're talking about that is happening between an AP and station, in some ways also need to happen across APs. Right? Which is again, I don't know how well and how soon these will be implemented, but in theory, they look really, really nice and cool to actually understand. So the technology is cool. We'll have to see how well it's going to be implemented. Okay, so we have these are some of the Mac features. We also have a few other things like what we refer to as hybrid automatic repeat request, or hybrid ARQ is another technique that is used in Wi-Fi 7. So if you look at the normal method in which a transmitter communicates to the receiver, a transmitter can send a data frame, and let's say receiver is not able to acknowledge. An AP is sending a data frame, the AP station is not able to receive it well because of some signal to noise ratio issues, because of low RSSI, because of poor link connectivity, whatever it might be. It's not able to acknowledge the transmission. So normally what the AP will do is the AP will say, oh, okay, so I did not get the acknowledgement, which means that this guy must be out of my range for that particular MCS rate. So let me do exponential back off. And then next transmission opportunity I'm getting, I'm going to drop the data rate to a MCS rate to a lower rate so that I can communicate well with the station. And then the retry, the station can possibly acknowledge that packet. That is a standard method that we use. Right? In the hybrid model, what happens is when the AP sends a packet and the packet is not received well by the station will not acknowledge it. But then the AP, instead of dropping its lower MCS rate to a lower rate, it can decide to transmit to the same rate, right? And then let's say that packet is also not received by the by the station. What the station can do is it can keep a copy of the previous packet that was not received, right? And it can combine the two bad packets to actually put them together to figure out if it can actually figure out it can do the forward error correction and get the actual packet. Right? And so if you keep the previous copy and combine the previous copy with the current copy, then you might get up to a 4 to 6 dB gain in the signal level, right? And so this allows the transmitter to not rate scale. It doesn't have to necessarily rate scale and more efficiently use the medium. Again, computationally, this is a lot more intensive because we are talking about taking multiple packets and processing them in a SIFS interval, like 10 microseconds, right? Again, I don't know how practical it is to implement, but in theory, it sounds very good, and it can improve the efficiency. There are also some enhanced methods when it comes to quality of experience. There is things like enhanced QoS that are part of the Wi-Fi 7 standard. Here, this is again for devices or stations that have deterministic traffic, where the AP can announce certain restricted service periods, where the station who are members of that restricted service periods can transmit. It is in some ways like the PCF model. And so there are restricted service periods. So anyone who's not part of the restricted service period has to stop when the restricted service period starts, so that only the members of the restricted service period can transmit during that time frame. And this makes the transmission of devices that require basically deterministic slots to actually transmit and reduce latency. So there's enhanced QoS methods that are available as a part of Wi-Fi 7. There's also another feature which is being proposed across multiple Wi-Fi standards. This is called a peer-to-peer transmission, especially in use cases where, let's say, you have a phone that is trying to cast a video to the TV, or you're trying to do some local VR applications, or you're trying to do some wireless file transfers between two devices. So that's what we refer to as peer-to-peer communication. We want two devices to talk to each other without having to communicate with an access point. So if you want a transmission, so the AP can send a MURTS frame and announce a peer-to-peer connection between two stations, and then the stations can kind of then use the directly communicate with each other, right? Again, I don't know if this is going to be implemented anytime soon, any of the implementations, but that is one of the features that is under consideration standard. So just to summarize, we covered a number of features, new features relating to Wi-Fi 7 physical layer improvements, 320 megahertz, 16x16 MIMO, and 4K QAM, and preamble puncturing, and multi-RU support. All of these makes the physical layer. At the MAC layer, we have MLO, we have multi-AP coordination, we have all these other hybrid QoS and other methods that are there. Not every one of them will be used, and all these features are designed for a wide variety of applications and use cases. So not everyone would implement all of them, but there are features like 4K QAM and 320 megahertz, and also MLO that are already being implemented. And from all the Wi-Fi 7 APs that we have worked with, we have seen all these features working to some extent. Right? So to learn more about all of these different features, again, it's hard to cover all of that in 1 hour. So you can go. There are a number of really cool papers and YouTube videos and so on that explain all of these things in fair amount of detail, and you can certainly go watch all of them. So this concludes this module where we have covered all the Wi-Fi protocol extensions all the way up to Wi-Fi 7. And then the next module, we're going to talk about more business use cases for Wi-Fi. At this point, a lot of the technical part is mostly covered. And then we'll talk about the business side of Wi-Fi a little bit. And then we'll come back to testing and debugging tools and all of that for the rest of the course. So I hope you enjoyed the session.